Welcome to this next third session of the electromagnetism module. This time we are going to speak about capacitance and dielectrics. In the end, we will speak a little bit about metals. So last time we already discussed that happens when you have two parallel plates. How does the electric field of that look like? So essentially, a capacitor is two conducting conductors separated by an insulator. This insulator can be vacuum or can be any material, and that's it. So whatever we discussed last time is essentially connected to capacitors. We have a wire, we have a plate, which we call A and B here, and there is a d distance between these two plates. We have plus q charge on one of the plates and minus q charge on the other plate. And that will be a potential difference between these two things, and so that's what we call a capacitor. If we want to have like a representation of this in a circuit diagram, we either see this two parallel plates essentially connected to it, or sometimes in the British literature you may see that there is a curvature on one of the plates. A capacitance is a property of a capacitor. We usually denote this with the letter C, and so we define this as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between the conductors. So in notions, this is going to be Q over delta V. So it's a measure of the ability of the capacitor to store energy, and by definition, this is going to be always positive. So this was named after Michael Faraday, and the SI unit for this is the farad. We use the letter F for it, so the capacitance uh, C. This is not the coulomb, right? So this is C for capacitance. The unit of it is farad, which is the coulomb over the volts. A farad anyway is a very large unit. So in real life, you don't really see anything which is even like close to 1 farad. The typical devices range from microfarads to picofarads. So let's just again discuss this situation when we have this parallel plate capacitor. As I mentioned earlier, we have two plates, metallic plates, and let's have them both an area of A and separate them with the distance D. As earlier, we will have plus Q charge on one side and minus Q charge on the other side. And by the definition of the surface charge density, we get this sigma to be the charge Q divided by A, because that was the area. So the question is, what is its capacitance then? The value of the electric field is something that we already discussed earlier. Last time we calculated that the electric field is the sigma over epsilon 0, and sigma was now defined to be Q over A, so the electric field is going to be Q over epsilon 0 times A. And since the field between the plates is uniform, the magnitude of the potential difference between the two plates is just going to be, we already earlier discussed that this is the line integral of, of the electric field, but because of this uniformity, the vectors are showing in the same direction, and so we can take out the E, and then the integral of the delta or the d, right? So we call the distance with d. So if I take a partial part of it, an infinitesimal part of d is going to be the dd, and if I integrate the dd, I will get d. Essentially, it's going to be just the multiplication of the electric field and the distance d. So I just add an extra d to this e definition, and that's how I got the delta v potential difference. The question was about the capacitance, which we defined to be the ratio of the charge and the delta V. So now, including our latest information about delta V, we get that the capacitance of these parallel plate capacitors is going to be the epsilon 0 vacuum permittivity multiplied with the area divided with the distance between the two plates. So that's our end result. So please note that this means that the capacitance of the The capacitor is proportional to the area of its plates, and it's inversely proportional to the plate separation. And we have the constants, epsilon 0, which is less important. Alright, so let's just go into a bit of problem-solving strategies. As earlier, it's always good to make a drawing showing the electric field lines, and if there is symmetries like we had it here, that the electric field showed in the same direction, that makes the situation a little bit simpler. So exploit any symmetries if there are any, calculate the electric field, and calculate the potential difference, and then use the definition that the capacitance is the ratio of these two. And so that's essentially the way how we solve problems for capacitance. So let's now go into this capacitance of having a shell. So we have a solid cylindrical conductor which has a shell, a radius of A, and then we have a shell which has now which is located at the radius B. And so let's just say that this shell, we call it a shell because it has a negligible thickness, and we put plus Q charge in the red solid conductor and minus Q charge in the shell. And we are asked about the capacitance, and we also know that the length of this capacitor is L. So making the drawing is something that, well, so this drawing was just about the situation, but the drawing should be about the electric fields. So let's look at this whole situation from the top, and we know that we will have we kind of discussed this electric field of a line, but so the point is that we have radial electric fields, and then the Gaussian surface could be this dashed line, and so we know that this has a cylindric system, so it has a cylindric symmetry which we will use. And as I mentioned earlier, we already figured out how the infinite cylinder looks like, the electric field of an infinite cylinder looks like. So that was this one-dimensional charge density lambda divided with 2 pi epsilon 0, and then we remember that it was essentially really dependent on the distance, which we called r, and so it's an inverse relationship. So in the end, the electric field goes with the lambda over 2 pi epsilon 0 with the 1 over r. And again, you can ask, do we really have an infinite cylinder now? And so, the answer to this is that this is all just depending on how close we are looking at the system. If these things are much, much bigger than other dimensions of the system, then we can consider this to be something that's infinite. So earlier, the potential difference is defined to be the negative line integral of the electric field. So that's what we do. We know that the electric field is radial, and we also know that the line integral takes the same direction. So that means that this is going to be somewhat simple. We can get rid of the vector notion. And we also know that the electric field in this radial direction is what we calculated earlier. So now we have an integral which has constants in it that we can take out, and we are left the integral of 1 over r by r. So we know that the integral of that is going to be a natural logarithm. So that means that we have minus lambda over 2 pi epsilon 0 times the logarithm, and then we include the boundaries of the integral, which were b and a. So that's what we have in the end. This is the natural logarithm of the ratio of b and a. So now we want to calculate the capacitance. Reminder of the definition. The capacitance is the charge divided with the potential difference. So we now calculated the potential. The charge was already given, but essentially it was given with the no, it was given as a q, right? But so then what we have to figure out is how do we relate the lambda to the q, and so we know that lambda is the one-dimensional charge density. So that's going to be the Q over the L, because that's the dimension in which we are given something. So these Q's are cancelling each other. The L goes to the numerator, and in the denominator we still have the 1 over 2 pi epsilon 0 times the natural logarithm of the ratio of B and A. And that's the answer. This was a question about the capacitance. So this is the final answer to this question. Another problem which is very similar, but I'm not really going to go through it, but just give you hints. So we have a spherical capacitor this time, and then we're given a smaller sphere with a radius of A and a bigger shell, which is which has a radius of B, plus Q charge in the inner and minus Q charge in the outer sphere. And we're interested in capacitance. So again, we do the same thing, make the drawing of the electric field, figure out how the electric field looks like, and then do the integral so that you can find the potential difference, and then just use the definition of the capacitance to figure out what the capacitance of this spherical capacitor is. Okay, so now let's go back and combine these capacitors in an electric circuit. So we say that two capacitors are connected in a parallel combination if they look like what the figure shows. So that means that we have a circuit diagram for this, which is shown like this. We have a battery here that provides a voltage difference, and then two lines parallel to each other. As we said that the parameter for the capacitor is really the capacitance. So we have C1 and C2, and then there is Q1 and Q2 charges on these capacitors respectively. So then using the definition of the capacitance, which was that C equals Q over delta V, we can express Q from this, which is going to be C times the delta V. So the charge on the first device is going to be the capacitance multiplied with the potential difference on the first device, and then the same thing on the second capacitor. The total charge in the system we should denote as Q tot, and so that is really just the sum of these two charges. So the Q tot will be the Q1 plus Q2, and including the definition of the capacitance, that will further equal to C1 times delta V1 plus C2 plus delta V2. So let's just say that we want to replace these two capacitors by an equivalent capacitor, which will have the equivalent capacitance of CEQ. So what do we do? Well, the total charge is then going to be the CEQ multiplied with the delta V, which is coming from the battery. So then that means if we want to replace them, then the CEQ delta V is going to be the same as the C1 delta V plus delta V1 plus the C2 delta V2. And so the outcome of this is that in a parallel system, the voltage difference will be the same. So that means that we can take out the V1 and V2 are the same. So we can take out that the equivalent capacitance is going to be the sum of these two capacitances. So in case when we have a parallel combination of capacitors, the equivalent capacitance is the sum of the individual capacitance. We can also combine capacitors in a serial combination. So it's in a series that means we connect them like this, and in the circuit we denote it like that. So let's look at this diagram on the right. In this situation, the left plate of the capacitor 1, so this plate, and the right plate of the capacitor 2 are connected to the battery, right? And then the right side of the capacitor 1, this thing, is connected to the left plate of the capacitor 2. So these two form an isolated system, which initially is uncharged and must continue to have zero net charge. So that means that when the battery is connected, the electrons are transferring from this side, and they move to the left plate of C1 and to the right plate of the C2. So then the negative charges leaving the left plate of C2 cause the negative charges to accumulate on the right plate of the C1. And then that means that if you want to have this isolated system, these two things, to have zero net charge, then if there is plus Q charge here, that means there has to be minus Q charge on the other side, or vice versa. Okay, so that means that the charges on the capacitors connected in the series are going to be the same. So the Q1 and the Q2 are the same Q. And this Q is the charge that is moved between the wires and connected to the outside plate of one of the capacitors. So then the voltage difference, the total voltage difference, is going to be the sum of the delta V1 and the delta V2, which we again calculate by the charge over the capacitances. And so then we have an equivalent capacitor in this situation that will have the delta V of dq over CEQ. And using this argument from earlier, Q1 and Q2 are the same as the Q, so we can just divide with that. And by that we get that the inverse of the equivalent capacitance is going to be the same as the inverse of the C, as the 1 over C1 plus the 1 over C2. So we can make this general, that 1 over CEQ, the inverse of the equivalent capacitance, is the same as the sum of the inverses of the individual capacitances. And then if you want to have a number for the equivalent capacitance, then we can just really take one more inverse of the situation. So that's going to be 1 over the sum of the 1 over C i's. And that's the equivalent capacitance for the serial case. Okay, so again, a little bit of problem solving skills. Let's again start with the drawing, showing the capacitor arrangement, and then we have to identify whether we have a series or a parallel connection. And when we have the capacitors connected in a series, they will have the same charge, and if they are connected in a parallel, they will have the same potential difference. In the end, you should check the answer. If you have a series connection, then the equivalent capacitance must always be smaller than the original values, and if you have a parallel one, then it must be greater number. So a little problem, which I'm not really going to solve, it's somewhat simple. We are looking for the equivalent capacitance between A and B. So we have both parallel and we have both serial connections here. We are given the capacitances to be 3 microfarad, 11, 12, and 6, and then 9. So the way to solve this is that we look at subsystems. So first we just look at these two. These are connected in a serial one, so we know how to calculate that. We will do that. And then we have a system of 3 capacitances which are in a parallel system. We also know how to solve that, so that's going to be another box now. And when we have the equivalent capacitance for that, then we just have 2 serially connected capacitances, and we also again know the rules for that. So after we have done that, we know the final answer to this question. So I mentioned earlier that what capacitors do is that they store energy. So how do we calculate this energy stored in a capacitor? So we know that the positive and the negative charges are separated in the system, and so there will be an electric potential, and this electric potential stores energy. We could have a switch which we open, and then the capacitor remains uncharged, but there will be still some electric field between that 2 points, because there will be electrons flowing in being on the left plate, And because of this separation, there will be an electric field, and that electric field will store energy. So let's just say that we have Q charges on the capacitor at some point, and we are interested in the potential difference, so that's going to be Q over C. And we are now interested in the work that's necessary to move this little increment of this charge, which we call dq, from one side to the other. So the work is calculated as the delta v times delta q. It's the integral of the potential. You may remember this when we discussed the definition of the potential. And so we know that the delta v was q over c, and inserting this information, we get that the infinitesimal work is calculated to be the charge over the capacitance and the infinitesimal charge. Of course, we are interested in the full work, so what we are going to do is that we are going to integrate the infinitesimal information. So we will move the full charge, right? The full charge was q, uppercase q, and originally we had 0, so the integral boundaries are coming from 0 to q. Capacitance is a constant in this number. It doesn't depend on the Q. As remember, the capacitance just depends on the parameters of the capacitor. And so we can move that out from the integral, and then we get the simple integral of a single variable, Q, for the first power. We know that those have the primitive function of the second power of that thing divided by 2. So that leads to 1 over c times q squared over 2. The work is the same as the potential, the electric potential, so that's going to be q squared over 2c. And playing a bit with the definitions of the capacitance, inserting that capacitance was the q over delta v, we can get the work, or this energy stored in the potential, as 1 over 2 times q times delta v. And again, just playing with the same definition again, we can say that this is 1/2 times c times delta v squared. So let's put in what we have learned for the parallel plate capacitor. We learned that the capacitance of the parallel plate capacitor is epsilon times A divided by A. And we also learned that the potential difference after we do a very simple line integral is going to be E times D. Let's turn into the second power, which then means that we have that this energy stored in the capacitor is 1/2 times epsilon 0 times A times the distance times the electric field squared. So if we define an energy density as the energy per unit volume, right? We were discussing charge densities, which were charge per volume. Now energy density could be defined in the same way as the energy by the volume. So let's just call this energy density to be lowercase u, and because it's for the electric field, let's put an extra e into the index. So that's the uppercase u divided by the volume, which we calculate as the area times the distance. So that means that if I include this ue, lowercase ue, then we will get that all the a and the d are taken out from here, and essentially this energy for the electric field is going to be 1/2 times the epsilon 0 times the electric field squared. And although we were saying here that we were doing something with the parallel plate, this expression is really valid for any source of electric fields. So I mentioned earlier that you can put in some material between the capacitances, so let's just discuss dielectrics a bit. Dielectric is a non-conducting material. It could be a lot of things, rubber, glass, or box paper, for example. So that's something that you can now insert in between the two plates of the capacitor. And so again, we have a charge of Q0 and the capacitance of C0 in this capacitor. And if we now insert this dielectric, then and measure the voltage difference between the two plates, then what we see is that the capacitance will increase by a factor, and this factor is denoted with the kappa, Greek letter kappa, and it's called the dielectric constant. It's dimensionless quantity, and so you can say that the final capacitance of the capacitor will be kappa times the C0 original capacitance. So just to go with a bit of real life problems, every time you push a button on your computer or your keyboard, then you use capacitors. Because the keyboards work in a way that there is two plates and some insulator in between them. And as you push down the button, then the distance between these two will move. This is like some flexible insulator here. And because of that, the voltage difference will change, and that's how your computer knows that you push the button. Every time you use any kind of app that measures your velocity or like your location, those use gyroscopes. So there are like at least 3 gyroscopes in your phone, and as you brake, for example, that means that one plate of the capacitor moves, and the same situation happens, that there is a voltage difference that's recognized by the system. And that's how you know that you are slowing down or accelerating. There are usually two kinds of physical capacitors in a circuit, either like these black cylindrical ones or these kind of ones. These have different colors too, but the shape is usually like this. So these are like something on the left, that you have a metal foil and there is paper in between them, and then you are just rolling it up, because this is the way how you can have big capacitances in a very small plate, right? So this was actually really very sort of like 3 millimeters or 2 millimeters, this black part, and or even maybe less, 1 millimeter. No, I don't think it's more like 2 millimeters, I would say. But like, so this is how those really work. And then there are like big capacitors outside, like like data storage facilities where you really cannot lose power for very long. So these have these huge containers in which they fill it up with oil, and that oil is what we use as a dielectric to increase the capacitance of the system. And so that's how those work. Sometimes we also use this metallic foil with an oxide layer, and then there is a outside case, and there is some electrolyte, um, some material that is used, which is better than the paper. So I said that we should discuss a little bit about metals. So going on to Faraday cage. Faraday cage is a very interesting concept. It's a metallic body that prevents the entry or the escape of an electromagnetic field. The ideal Faraday cage would be an unbroken, perfect conducting shell, but usually this cannot be done. And what people do is that there is some fine meshed, usually copper screen. And if the cage is connected to the earth, then it works very nicely. I put here a link to one of the MIT electromagnetism modules in which the professor goes into the cage, and yeah, well, I shouldn't really spoil it, so you should just check out the video. But also there are things like a plane getting hit by lightning. So nothing really happens inside because the plane acts as a Faraday cage. I will put here the links to the video on YouTube, and it's very interesting that you have this shell and then it conducts the electricity without touching anybody inside of the body. One more thing is that about curvature effects. So if we have two balls connected with a wire, first ball has a radius of RA and the second one has a radius of RB. And then since they are connected, that means that we are equipotential, that potential is the same. and we know that how we calculate the potential. We will put the potential for the A ball is going to be the charge in the A ball divided with 4 pi epsilon 0 times the radius of the ball A. And as I said, that's the same as the voltage on the potential on the other ball, which is denoted as VB, and that's calculated as QB times 4 pi epsilon 0 times RB. And so we have a lot of common factors here. We can divide or multiply with the 4 pi epsilon 0 and just get that the ratio of the charge and the radius is fixed. I mean, it's not fixed, but there is a rule for that. So if you have an object which has more curvature, then there will be higher charges on that. Right? If this number is bigger, then the only way that you could have this is that if you increase the the charge. And so that's all for today. Please let me know of your questions, and if you like the video, then hit the like button. Thank you, and see you next week.